Thank you for the introduction, and thank you for this great opportunity to present to you today. I'm Hiroshi Hayasaka from AIST, Japan. Today, I will talk about the general methods to construct in-field counter-diabatic drive for quantum annealing. The collaborators are Dr. Inoto, Dr. Masaki, and Dr. Kawada. This talk is based on the result obtained from the NEDO project. First, I will explain a bit about quantum annealing. Quantum annealing is known as a computational method using quantum fluctuation to obtain a non-trivial ground state by using adiabatic time evolution, starting from the trivial ground state of the well-known Hamiltonian. Quantum annealing Hamiltonian is given by this form, and the HP is problem Hamiltonian, and the HD is driver Hamiltonian. The solution of the problem can be embedded in the ground state of Ising Hamiltonian. To obtain this non-trivial ground state, we gradually decrease the strength of the transverse magnetic field, and while we gradually increase the strength of the Ising Hamiltonian. If the adiabatic condition is satisfied, the population of the initial states remain in its ground state of the quantum annealing Hamiltonian. In recent years, the application of quantum annealing for field of material science has been attracted much attention. For example, quantum chemistry is one of the important applications of quantum annealing. Typically, we need the exponential resource to calculate the electric structure of molecule on a classical computer. So there is a substantial effort to compute such problem using quantum computing, also including quantum annealing. In the field of condensed matter physics, the spingless states and Austerlitz-Thouless transition have been observed on the Diego annealer. So these demonstrations means that quantum annealer has a potential to explore the many-body physics, and it can be expected that the quantum annealer can be used as a quantum many-body simulator. And so in such a background, we interested in how we can perform such simulation and quantum state preparation in short annealing time. One of the methods to address this issue is counter-diabatic driving. Counter-diabatic driving is known as a method for completely suppressing non-adiabatic transitions. So it can achieve the adiabatic time evolution in a short annealing time. This can be achieved by adding the control field to quantum annealing Hamiltonian, such that the system remains its adiabatic state, which is a solution of this Schrödinger equation. Here, Kn is the instantaneous eigenstate of quantum annealing Hamiltonian. So if we solve this Schrödinger equation, the fidelity between the instantaneous eigenstate of quantum annealing Hamiltonian and the solution of this Schrödinger equation is always 1, even if the annealing time is short. This control field is referred to as the counter-diabatic term. However, the construction of counter-diabatic term in many-body systems requires non-local interactions, so it makes experimental implementation difficult. Moreover, there is a need to know the exact energy eigenstate of the many-body system during the annealing process. So to to avoid these difficulties, the bias method using such variational method and mean field approximation to construct counter-diabatic term have been proposed. The advantage of this method is the counter-diabatic term can be expressed as a local form, and we don't need to know the exact energy eigenstate in advance. In this talk, we focused on the mean field approximation for counter-diabatic term. The mean field approximation for the counter-diabatic term has been proposed by Hatomura. His previous research has mainly focused on the uniform ferromagnetic Ising model and has not addressed the case of the antiferromagnetic model or non-uniform interaction. More interesting and practical problem arise when the interaction is non-uniform or antiferromagnetic. So namely, the frustration and disorder play a crucial role. And it is unclear whether the mean field approximation can be applied to such a general interaction. So in our study, we investigate the construction of more general mean field counter-diabatic terms. First, I will explain the difficulty of mean field approximation in general interaction model. Let's start to consider the antiferromagnetic Ising model with a uniform nearest neighbor interaction as an example. In this system, the ground state is classical naive state. To find this configuration, we need to solve simultaneous equation for each sublattice A and B, which is a relatively easy problem. However, if the interaction has non-uniformity, like spin glass, we have to distinguish the magnetization for each qubit because we don't know in advance what configuration realize due to non-uniform interaction. So we need to solve N-nonlinear simultaneous equation at each time step because the right-hand side of this self-consistent equation depends on the magnetization for as a all side. So it may become computational bottleneck. To address these problems, we propose another method for constructing mean field counter-diabatic term by computing the mean field dynamics of magnetization instead of solving this self-consistent equation. This is a schematic illustration of the conventional quantum annealing and our method. Top figure shows conventional quantum annealing. If the annealing time is short, the speed precession around the effective magnetic field occurs, and then the fidelity decreases. On the other hand, in our method, we use the configuration of magnetization as initial condition for this differential equation. If we get the solution of magnetization, we also can calculate the effective magnetic field. And then we also calculate this mean field counter-diabatic term. This mean field counter-diabatic term expressed as effective magnetic field along y-axis, which can suppress this spin precession of magnetization. As a result, we can mitigate the reduction of fidelity. Next, we will provide more details of our calculation. First, let's start with an explanation of our problem. We consider quantum Hamiltonian like this. Here, HT is the problem Hamiltonian. We use quantum stimulus model as problem Hamiltonian. And the driver Hamiltonian is transverse magnetic field. And we use random longitudinal field to avoid the metastable state in classical dynamics. Here, Jij is the standard normal distribution, generated from the standard normal distribution, and Hi is the random variable, which generated from the uniform random distribution. And the scheduling function, ft and gt, are defined by a function with such a time dependence. To construct the mean field counter-diabatic term, we use the mean field approximation for quantum annealing Hamiltonian. And then we use the mean field approximation for the counter-diabatic term. And this term turns into the magnetic field of Y component. And then we calculate this mean field counter-diabatic term by using mean field dynamics. Finally, we can obtain this mean field counter-diabatic term. Next, we will show whether mean field dynamics corresponds to the solution of self-consistent equation. This figure shows the magnetization dynamics, and the horizontal line is normalized time, and the vertical axis is magnetization. Here we plot one of the typical realization of the random longitudinal field and random interaction. Solid line shows the solution of this magnetization dynamics, and dashed line is the solution of this self-consistent equation. So this result shows dynamics and self-consistent equation is same. Moreover, the Y component of the magnetization is always 0. So it means the magnetization dynamics is constrained in the XZ plane. So the spin precession is completely suppressed. Next, we show the results of the quantum annealing. Here, annealing time is equal to 1, and the system size is equal to 8. And we perform 100 samples for random longitudinal field. Both cases with counter-diabatic term and without counter-diabatic term. And we examined up to 30 samples for Jij, but all samples show the similar behavior. So therefore, we will show the typical realization for the Jij. First, we examined the fully connected ingress model, so-called Chilington-Patrick model. This figure shows the time dependence of fidelity. Here, the fidelity is defined as the inner product between the Schrödinger dynamics and the exact diagonalization of quantum annealing. In the case without counter-diabatic term, the fidelity decrease in all samples because the normal transition. On the other hand, in the case with counter-diabatic term, the reduction of fidelity is mitigated in many samples. In some samples, fidelity decrease, and this decrease indicates the classical dynamics of magnetization trapped in metastable state. And appropriate counter-diabatic field is not realized. But I would say, if we prepare the appropriate mean field counter-diabatic term by random sampling of longitudinal field, we can obtain the ground state with high fidelity. Next, we show the case of one-dimensional spin chains, which means the interaction has only first nearest neighbor coupling. This result shows almost similar behavior of pre-connected spin glass model. Typically, mean field approximation deteriorates in low-dimensional systems, but this result shows mean field counter driving will work despite in low-dimensional systems. Next, we will explain the implementation on DA for our result. DA annealer cannot implement our counter-diabatic term because our counter-diabatic term is proportional to the sigma y term. So we introduce the time-dependent spin rotation operator to eliminate this sigma y term. Moreover, if the Hamiltonian has non-uniform interaction, the non-uniformity appears in driver Hamiltonian through this spin rotation. So such an independent control for driver transverse field cannot be implemented in current annealer. So we consider a pre-connected antiferromagnetic model for the example of implementation on the DA annealer. This model has exponential symmetry in ground state when the longitudinal field is 0. If we add the longitudinal field to this model, the unique ground state appear. So, which slightly apart from the excited state. So it can be expected that this model has well captured frustrated nature, and we can expect that solving such model by using conventional quantum annealing is difficult. And we choose longitudinal field like this to realize the classical nail state as a unique ground state. After this spin rotation, the Hamiltonian is given by this form, where A and G prime is the scheduling function, which reflects the time dependence of the counter-diabatic field. And this is to such non-trivial annealing schedule. We also use linear schedule to compare the success probability obtained the classical nail state with the case of this case. This is the result. The red line is a case of mean-field counter-diabatic term, and the blue line is a case of linear schedule. This result shows that success probability becomes higher due to our counter-diabatic term compared to this linear schedule. This is summary of this talk. We propose a general and practical method to construct the mean-field counter-diabatic term, And we numerically demonstrate the quantum annealing with mean-field counter-diabatic term can obtain the ground state with high fidelity. And we implemented our method on the DF quantum annealer and demonstrated how high success probability can be obtained. That's all. Thank you for attention.
We have time for one or two quick questions.
Can you show us the equation for the local field dmi dt equal to mi plus b, the dynamics equation? Yes, is this a closed form equation in the sense that we can solve that equation without any recourse to quantum dynamics or any other external parameters? This can be solved by itself?
Yes, close
Then
equation.
why don't you do it?
Sorry?
You can solve this equation as a function of time and see the result of mi or
Yes.
at the final time,
Yes.
after t.
Yes.
And you know the answer without recourse to any quantum.
No. We use this solution corresponds to the classical configuration of magnetization, and we use the problem is like quantum model. So
Yes, I understand. But forget about quantum nature.
Yes.
You want to solve the classical
Yes.
problem.
Yes.
Then the dynamics equation
Yes.
is sufficient.
Yes. So I mean this dynamic equation can solve the optimization problem.
So
yes.
what's wrong about it? Why do you use quantum annealing?
I would say that our method can be applied to such quantum simulation or like state preparation. Or we focus on the application of quantum annealing for such material science. So
if your goal is to obtain the classical ground state of the classical Ising Newtonian, approximately at least,
yes.
then that closed form dynamic equation sounds like sufficient. I may be wrong, but what's your...
But yes, you know in the quantum system has like entanglement state or such a superpositional state, which cannot obtain from the classical dynamics.
So you're going to that direction, so the present results are the first state.
Yes.
Is there one more question over here?
Yes, okay. I'm just wondering, do you perhaps have any idea, any vague indication of how the time needed to prepare the counter-diabatic term and the fidelity that you obtain scale in the system size?
I have not yet such a scaling. So, but my naive expectation is for example, the system size is fixed. The fidelity is for example, the average of the fidelity becomes higher than the case of with a counter-diabatic term. So, which means that if the system size becomes larger, in the case of with the counter-diabatic term, the fidelity becomes larger than in the case without the counter-diabatic term. If the system size becomes larger. So, but such exponent of the exponent becomes a bit lower than without the counter-diabatic.
I see. Thank you.
Okay, let's thank the speaker again.